Okay, so we just seen that every Boolean function, every truth table can be coded by a formula which is only using and, or, and not, which means that every time you have a formula in logic which has implications, if and only ifs, what have you, you could write an equivalent formula which uses only and, or, and not. A very natural question is, okay, so whether and, or, and not is always enough? Do you sometimes need only some of them? Would you lose the ability to encode any table if you throw out any of those three connectives? So we call those sets of connectives, the ones that can encode any truth table, a complete set of connectives. So complete in a sense that if you look at all the possible truth tables, you could do them all. So the natural question is, how small can a complete set of connectives be? Is and or not the smallest one we could do? In fact, you may notice that and negation or a negation together already give you a complete set of connectives. One way of seeing it is if you think about our calculation for canonical CNF, there was one step when we took the negation inside by the first De Morgan, switching the outside ors to ends, but didn't yet take negations inside of the individual terms to make them clauses. At that moment in time, we had a formula which only had negations and ends, and yet it was coding up a truth table for pretty much an arbitrary function. So if we only have not an end, and similarly, if we only have only not an or, we could code up any truth table. But if we throw out negation, we would be in trouble, because every time you have two variables that are true, and you take an and of them or you take an or of them, both cases you are going to get true. So what if you want to take something true and make it to false? Well, with only and or, you cannot rewrite something with a negation and make something equivalent. In fact, you can go to less than two connectives if you change what connectives you're talking about. So if you throw out negation or you throw out and from the set of negation and end, then you're in trouble and you cannot code things. But if you take a new connective, for example, the connective called NAND, which stands for not and, then you could encode any truth table by a formula that only uses this connective. So engineers often use a NAND and this symbol to encode this connective. Logicians tend to write it as a Schaeffer stroke and write it as a vertical line. I will be using the vertical line just because writing is shorter, but it has the same meaning as NAND, not AND. So the truth table for that connective, the definition of that connective, is that it's false when both of its input are true, and otherwise it will be true. So if you take an or of your input and then negate it, you will get exactly the same truth table. Let's now see that you could simulate any complete set of connectives, and you could therefore code any truth table by just using formulas with only that NAND or Schaeffer stroke connective. And in order to do that, it's enough for us to show that you could simulate not, and you could simulate, well, either one of the and or an or, let's say or, using only this one. Let's do not first. So notice when both inputs to these connectives are true, the input will output, the connective will output the false. So we could rewrite not A for any possible formula A as A, not, and A. You could check for yourself that you end up with exactly the same truth table for two things. Both formulas will be true when A is false and false when A is true. Here's your equivalence. Now let's do the same thing for OR. Suppose you have a formula A or B and you want to rewrite this formula using only that not and of Schaefer-Stroke connective. So first, remember that it's called not and for a reason. So if you can rewrite your OR as not and, you could get away with one application of the connective. And so this is what we do by De Morgan. A or B is the same as not A, and not B. Yes, we got a longer formula, but now we could write this whole thing using just that connective on the two things on the two sides of the end, which are not A and not B. So wait a moment, there is a negation, and we don't have negation, but we just showed how to do negation. So in order to write A or B, we could write A not and A, not and of B not and B. And this will be an equivalent formula, and that uses just one single connective, which suggests that you could build circuit out of only one hardware element, the not and. So that said, in practice, and to make things shorter and simpler, most people stick to the set of three connectives of an and, of an or, and a not. And that's called historically De Morgan's basis. They're the same De Morgan as De Morgan's law. You could kind of see how those things come from the same area, the same thinking. Okay, so with this, we will be finishing the first part. We will be finishing talking about propositional logic, and after that we will start talking about more general formula, talking about more general concepts. And before we do that, here is a puzzle. So think about kind of a stereotype person like that. Susan is 28 years old. She is bright, outspoken. She majored in philosophy and concerned with discrimination, social justice, participated in demonstrations. You could fill in the other details of the stereotype. But here's the question that I want to ask you, and here's the question where I want you to think logically. There are following possibilities of who Susan is likely to be. And from knowing people, from knowing stereotypes, you could kind of take a guess which of those possibilities are more likely for her. Is she likely to be an insurance salesperson? Is she likely to be a feminist? So look at those 8 possibilities and try to arrange them from the one that you think is the most likely to the one that you think is the least likely. Is she likely to be an active feminist? Is she likely to sell insurance? Think about it, and we'll continue next time.